right, we're official. Good afternoon, everybody. I'm excited to be here. I'm more excited to turn the time over to our wonderful students. These are students from our fitness technician program, about ready to graduate, going to industry. We decided to do a project, some research on lactate threshold. So our research project is on lactate threshold analysis. We're looking at 3 different assessments: the actual blood lactate, we're looking at heart rate deflection, and we're looking at critical power. And we're looking to see if they are valid tools for exercise prescription analysis based off threshold determination. I'll turn the time over to Kylie.
So like Nate said, we are in the Fit Tech program at SLIC, and we're huge promoters of health. And an important part of health is cardiovascular fitness. And a way to test cardiovascular fitness is with through lactate threshold protocols. Blood lactate threshold is the gold standard for testing, but it is expensive and requires invasive techniques and expertise. So our question is, can additional field tests be used to determine lactate threshold for exercise prescription? So our hypothesis is that we predict that lactate threshold is not significantly different between blood lactate, heart rate deflection, and critical power. I'm turning it over to Angie now.
Thank you. I feel like I have 16 things in my hands. Okay. So we had 3 testing protocols, as been noted before. We have critical power, blood lactate, and a heart rate deflection, which is called the Conconi. We did all of these over a 2-week period on spin cycles in a controlled environment. So let's talk about blood lactate threshold. The definition of that blood lactate is when the threshold when the lactate within the blood, which is a metabolic byproduct of glycolysis, which actually produces the ATP that we need for the energy to move, it increases faster than the body can clear it out. And so, and it also due to the rate at which we utilize oxygen during prolonged anaerobic exercise. So the protocol that we did, the test that we did with our lactate threshold was we did a warm-up 5 to 10 minutes, going up to 50 watts, which is our power increment. And then we took our blood lactate level after 3 minutes at 50 watts. We pierced the ear and got the blood out and went through on a lactate monitor using the test strips to determine that. And then we increased our power or our watts 25 increments, and we did a 3-minute stage at each increment, taking the blood lactate after each stage until fatigue, until we just couldn't cycle anymore. So here it shows we have our blood lactate, and you can see where it kind of goes exponentially toward the end, because our bodies utilize the oxygen that we have, and pretty soon we can't keep up with the work that we're doing, so the lactate, or that metabolic byproduct in our blood, increases exponentially. This is a heart rate. This is what happens to our heart rate as we continue to exercise and increase the power that we have to do. So the pros of doing this lactate threshold are that it's very accurate. It's the gold standard, like Kylie said, out there in the fitness world, and it's physiological based, so it's not based on just perception of how you feel. It's actually, with the blood. The cons are that these lactate monitors, and especially the test strips, are very expensive, and it's hard to get the blood from the individual doing the cycling while they're moving. I did it, and it's very difficult to get that blood out, and so those are the cons of that. I'm going to turn the time over to Teresa.
Okay, I'm going to be discussing the deflection or heart rate deflection, also known as Conconi test. So with this one here, basically what we're looking for is where we have a deflection and the velocity of our heart rate and what the break point is of that heart rate. So we're going to have a slope variation. We're also going to have like a heart rate threshold. Basically, it's characterized by a distinct differentiation or deflection in our linear heart rate excuse me, relationship or how much work that our heart is producing while we're doing this. And also we're going to do this in increments until exhaustion. So as we start with this, we're going to do like a 15 to 30 minute warm up. We're going to keep our intensity relatively low to moderate. After about 1 minute, we're going to go ahead and increase that intensity, and we're going to start at 50 watts. And then we're going to keep increasing that intensity in 20 watt increments as well. We're going to hold each of that increment for approximately 1 minute, and then we're going to add a new power, and we're going to keep that power level between 80 and 90 repetitions per minute while we're on the bike. We're at that point, it's okay. We'll go ahead and record the heart rate after each minute, and we're also going to record the rate of perceived exertion. So if you're feeling 2, maybe you're not too tired yet, all the way up to 10 where you're exhausted. And then we'll continue that increment of 20 watts until you have reached that rate of perceived exertion of 10. So this is one of our graphs that we used. We're looking at the break point here of where the deflection is in our heart rate. The great thing about this is it's easy. It's fast, it's inexpensive, and it's non-invasive. We're not having to take anyone's blood, and it's something that you can do in the field. Some of the cons is you do need to have a heart rate monitor, and that may be a disadvantage if you don't have one of those. Also, you have to make sure that you have power consistency throughout the entire test to make sure that we get the results that we'd like. And I'm going to turn this over now to Chen.
Hello. Does this one work? Can I use this? Other one? Oh, I think I'm going to use this one because I'd much prefer not holding so many things in my hand at once. So the third assessment we did was the critical power assessment. And what this assessment was, it's the determines the hyperbolic relationship between power output and the time it can be sustained. So the way we gather the data from this assessment is we obtain it by putting the subjects through an exhaustive all-out effort by the subject for a continuous 3-minute ride on a spin bike. Now, to get accurate data, the spin bike is actually connected to an ergometer, which is an apparatus that measures work and or energy expended during a period of physical exercise. Go ahead, next. The protocol for this assessment is that we start off with a 30-minute warm-up ride with our intensity between 40 to 60% of our VO2 max, which is basically an easy to moderate ride just to get the blood going, to get our muscles stimulated, to get our fibers working, so then we can really push an all-out 3-minute effort at our all-out intensity max. And with that 30-minute ride, it's followed by a 5-minute cycle at 100 watts, followed by a 30-second hit at the subject's max power, with keeping our rates per minute, so our RPMs between 80 and 90 RPMs. After the quick hit session, just to get, like I said, the muscle fibers stimulated and our metabolism really working, after the 5-minute and the 30 seconds, we go into the assessment itself, the 3-minute ride. So after the 2 rounds of the hits, the subjects endure an all-out high-intensity 3-minute ride. Here, the subjects are pushing between 80 to 90 RPMs and 120 to about 800 watts of power, depending on the individual's power capacity. And then to end this protocol, we end it with 5 minutes of moderate intensity cool down, just to help clear out, the lactate that's being built within the body and the fatigue. Next. So the graph here shows at the very beginning, we have the power output from 0 to 900 watts, and then we have the time frame of 0 to 180 seconds. What you're seeing here is at about 760 watts there. That's how much the subject begins pushing from about 0 to 15 seconds. So the minute the time starts, the subject's pushing about 760 watts. And the subject is able to hold that for about, as it shows here, between 15 to 30 seconds at most, and then the wattage begins to decline linearly. And so that's how that looks like. The pros of critical power is that it's a short assessment versus all the other ones that we just listened to. It's 3 minutes versus 30 to 45 minutes. Who wouldn't want to do a 3-minute assessment? It's very minimal equipment. You need a spin bike that has a meter that will collect all that data for you, that collects the work data, the power data, and the energy data. So most places will have that. And the cons of the critical power assessment is the intensity for 3 minutes is exhausting. You know, you hit fatigue extremely quick. It's a very advanced level of fitness, primarily used for cyclists. It's a assessment primarily for cyclists. And there's a longer recovery period between the assessments. And it can only be performed on a cycle or on a cycle bike with the meter. Otherwise, you wouldn't be able to collect the accurate data. And I'm going to turn the time over to Miena. Thank you.
Okay, I'm too short. Okay, so I will be letting you know about the data we gathered. Our first test, our lactate analysis, the LT, we first determined our lactate threshold, and based on lactate threshold, we determined the heart rate at LT. We looked at lactate breaking point, LT2, and what heart rate and power was at LT2, as well as the percent max heart rate and percent peak power. With heart rate deflection, we looked at our actual heart rate deflection, which should be similar to LT2, which is our heart rate, and the power at the deflection point, which should also be similar to the power at LT2. We also analyzed percent of peak power and percent of max heart rate. Analysis of critical power, which is the last one, does not require heart rate, so we took data just for power. We analyzed 2 3-minute trials, critical power 1 and critical power 2. We then averaged our critical power data at 85%, which we took from literature, which again should be similar to the power at threshold. This is the power analysis threshold that we got. The mean for lactate is 163.7. For heart rate deflection is 186.2, and critical power 173. And the standard deviation, which was quite large, gave us 59.5 for lactate threshold, 51.6 for heart rate deflection, and 88 for critical power. We ran a pair t-test statistical analysis for heart rate versus lactate, and alpha was set at 0.05, and we found a significant difference at 0.02, which supports the null, but heart rate versus critical power and lactate versus critical power supports our hypothesis. That is when we decided to look at the peak power percentage at threshold and the peak heart rate percentage at threshold to see if that was statistically significant. And we found that alpha was 0.31 and 0.27, which was not significantly different, and supports our hypothesis. And I will hand it over to Angie.
Thanks, Miena. So to kind of sum up just a little bit in our discussion, the heart rate deflection curve is an extensively researched and been validated many times. So we expected that our findings were going to go ahead and parallel all the previous research that had been done with regards to lactate threshold and heart rate deflection. But as Miena had just said, as we further analyzed it, we discovered that there was a lot of significant differences, but we did find a non-significant difference in the percentage of the peak power output and the peak heart rate. So that led us to go ahead and believe that we probably need to do more research and that there were other factors that contributed to the outcome that we got. Teresa?
Some of the other factors that we found was that with the fatigue, we needed to have more of a 48-hour rest in between these bouts of exercise. We also realized that we had different fitness levels, and it was also some of it was sports specific. Some of us are runners, where some were cyclists, and so that may have played a part in some of the data that we received. Also, our natural heart rate fluctuates. So if we took our test in the evening and then took another one in the morning, our heart rates are going to be different throughout the day. Our sample size was a little bit smaller than we have liked. We only had 6 in the sample size, and also we lost 3 participants during that protocol.
And then for our future investigation, if we were to do this again, which would be ideal, just to get more information, more accurate data. Like Teresa had mentioned, it would be a sport-specific. We'd gather sport-specific individuals, whether we're going to be testing on a treadmill, we'd get runners. If we're going to test on a spin bike, we'd get cyclists, just because when it comes to sport-specific, as you know, we saw within each other, some of us did better than the others because some of us were runners instead of cyclists. More subjects would be ideal. These were all of us. And so to get more accurate data, it'd be a better idea just to get more subjects. And she did mention that we did lose a couple, but in the future we would, gain a couple more. And then our recovery period is a very important factor to look at as far as tracking our sleep. We all would need to track the same amount of sleep and recovery period in between each bouts of exercise, just so then the body would really recover optimally. And then really look at or the time of day that we're testing, because we know that the diurnal cycle does play a part in the way we recover and where our heart rate fluctuates, because we know that later in the day our heart rates are greater than in the daytime. When you're waking up, heart rate's fairly low, and so later in the day, in the evening, we've already gone through school, we've gone through work, we've gone through stress of teachers, other students, kids, family, like we've gone through it all. So heart rate plays a big role, and being able to test at the same time of day every day would give us just more accurate data. Thank you so much for this opportunity. Now we open up for a Q&A.
Sorry, is that better? Sorry. So when you compare your VO2 max to lactate threshold, they're very similar, but they have a different capacity or a different basis in them. And so what you want to do is you want to increase your VO2 max as well as your lactate threshold, which means that you can put more energy out there without fatiguing to the point of not having enough oxygen or having all the lactate that your body can't clear it out fast enough and you fatigue faster. Does that answer your question?
So VO2 max is genetically tapped. So you're going to have about a 15 to 20% VO2 max capacity increase in training. So the key is with training and performance is we want to continue to enhance lactate threshold capacity, while after a while you're going to tap out your VO2 capacity. So your VO2 is going to kind of plateau out after some training. But lactate threshold, we can continue to enhance it. We want to shove threshold up. So we want to continue to push threshold up, like Angie said. So that, because that means if I take threshold and it happens at 8 miles an hour, and I can take threshold and make it at 10 miles an hour, now I can run a 5K at 10 miles an hour instead of 8 miles an hour. But your VO2 may stay about the same. So when we start to adopt exercise, we see increases in VO2 for a time, but then our VO2 is going to plateau out after a while. VO2 is your oxidative capacity, so your maximum ability to utilize oxygen. So we use VO2 values in the cardiac clinic, and we use VO2 values with professional athletes. So VO2 value is an indicator essentially of your engine capacity. Oh, good question. Not necessarily. So if you take a runner and they train as a runner and you put that runner in the pool, they'll probably have a lower VO2 in the pool. If you take a cyclist and you put that cyclist on a rowing ergometer, they're probably going to have a lower VO2 on the rower than they would on the bike. So it's very sports specific. We typically test kind of standard VO2s on, there's a lot of treadmill protocols that we use. Well, because treadmills elicit more muscle mass, and muscle mass elicits oxygen consumption. That should then elicit a higher VO2. So a lot of times if you take a runner and put them on a treadmill, you'll get a similar VO2 unless they're like a pro cyclist.
Okay, so certain things you want to do before testing, and that's what's important, not necessarily time of day. For time of day, it'd be like the same time of day every day. So just like getting enough sleep, eating a few hours before, not drinking caffeine, not coming with a hangover, just not necessarily time of day, but consistency.
Just a fun note, red blood cell count is the highest in the early afternoon. So if you want to maximize O2 adaptability, early afternoon might be the best. But you're right. Consistency in behavior is most important.
In the test they did. In the analysis they did. What just happened, schoolwork got into the way, lifestyle happens, things happen in life to where these participants just couldn't keep up with the test and couldn't keep up with the times that we were meeting to do this test. So they just opt out of it, and we decided to continue on with it because we were really interested in finding what the results were. So no, they're still kicking somewhere. Any other questions? Thank you.